code. And let's start. So we discussed the notion of group object in a category, or in general, like the object in C, and specifically group object in a category C. And this is also a useful notion. It have many interesting examples. So if C is topological spaces, then we get topological groups. If G is smooth manifolds, we get Lie group. If G is algebraic variety, we get algebraic group. If C is a category of schemes, then we get group schemes. So we can get many interesting examples. Oh, now people coming. Good. Oh. So now here is one example which probably is not that good, but not for group object, but vector space object. So one could expect that vector space object in topological spaces will give us topological vector space, but how Guy just commented, it doesn't really work. So it works in some sense. So if we have a field F, so F vector spaces, so we have the category of F vector spaces, and now we want such objects in topological spaces. We'll get topological vector spaces over F in the abstract sense. So we have addition and we have multiplication by a scalar, and the addition will be continuous and the multiplication by a scalar will be continuous, but without any topology on F. So more it's equivalent to just saying multiplication by each particular scalar will be continuous. But if we want to take into account the topology on F, this will not work in this way. So of course there is if F is topological field, there is a notion of topological vector spaces over F that takes into account the topology of F. So we want that the product map like this will be continuous. And in fact, it's possible to do also in the language of category theory, but not that simple. It's not just taking F vector spaces because F vector spaces in top because it cannot take into account the topology on F. And but still we can use it as kind of starting point. Yes, so we have the topology of F vector space object in top, the category, sorry, of this category, and topological vector spaces is some full subcategory of this category. Yes, I'm pretty sure it's full. And similarly, you can do with vector bundles. So you can consider the over category of X. Yes, so this recalls that this is over category, say over category of topological spaces in X, and consider what are vector spaces objects here, and vector spaces objects here, say R vector spaces objects here. There will not be vector bundles, but vector bundles will be some full subcategory of that category. So it still can help us with the first step. And of course, we can take here not just over category, but the category of fiber bundles, and it still will not give us real vector bundles if we will consider our vector space objects there. But again, we will get something closer and like smaller full subcategory. At the end, we can actually get the category that you want. There are like categorical ways to describe it, but are significantly more complicated.
Rami, can you describe this category again, the topics, and how is it a vector space object? What are the rules and
So,
what is the additional rules?
what category do you want me to describe again?
Topics, you said, right?
Topics is just the over category of X.
So what
So
is
it's just a
the
collection of all pairs, topological space Y and continuous map to X.
so what is a vector space object? R vector space object
I want to test something.
in this category?
So our vector space object, it will be so you will have an object over X. You will have an addition map like this. You will have a multiplication scalar map, but okay, for any scalar alpha, you will have a multiplication scalar alpha from Y to Y over X. And the vector space axiom will be satisfied. So this means that over each point in X, we actually get a vector space. But this is it. We will not get. It will not be actually vector bundles. So vector bundles will be some full subcategory of this category. So this I give as example of limitations of this language of taking C category in in D. So you cannot, you cannot directly define with this language the notion of vector bundles. Although it look like something like vectors, family of vector spaces over X, and family of topological spaces over X is just the over category. So it's tempting to think that just vector space object in the over category will give you vector bundles, but it doesn't work. It gives you something more general, maybe too much more general, and you can make it. You can find the subcategory of vector bundles inside it, but no, or at least not easily in categorical terms. Yeah, you actually need to know the definition of vector bundle. Yes, that's it. Answers
Yes, yes, thank you.
the question. Yeah, I wanted to write here capital X. Okay, so last time I gave funny exercise. What is group objects? Object in groups. So everybody solved this exercise? Somebody didn't solve this exercise? Yotam, I saw your lips moving, but I didn't hear anything, and now you're muted. Now it didn't work. Still not hear you. Not hearing you. Okay, your microphone doesn't work. Okay, never mind. No, that doesn't work. Okay, if it's something important, you can write it on chat. So the answer is a billion groups, and basically the actual statement is here that if you have two actions, two like multiplication actions that commute with each other, or in fact you only need one of them to compute with the other. So you have group G and another product map like this, which is homomorphism. So it means that first of all, M coincide with the actual product, and secondly, that both of them, M and dot, are commutative. Yes, so this is nice to know. And I can say some kind of application of this. So the fact that pi2 is commutative. So do you know what is pi2?
No.
What? Oh,
No, don't know.
you don't know. Okay, so I will tell. So what is pi1? Do you know?
Yes.
May I have a question just about what you said before? This is not the only axiom. There are more axioms.
There are more, but this is the most important one. You want M to be actually a group structure.
So
And
what do you mean by commutative?
This is the statement. So the theorem is like this. So assume G is a group, and you have another map M from G times G to G, which is homomorphism, and which gives it group structure. Then M is just equal to the multiplication, and they are both commutative. So and G is commutative group.
It is the solution. It is the solution, right? It's not איך
This
אומר?
exercise is more or less
Okay.
equivalent to the original exercise that group object
No,
in group has to be a
I'll
class
just
group.
okay. It's not a definition of a group object. This is
Yeah,
not.
group object in group does not. Yeah, you don't need those two steps.
Okay.
You just need this,
Okay.
and you need it a little bit more. But in fact, this is already enough. Group object in group it means that it's group, but also you have another group structure that might be different and might be the same. And a priori it might be different, might be the same, but a posteriori it has to be the same. And moreover, they both have to be commutative. So maybe I will not say why pi2 is commutative. I will say something very similar. Why pi1 of a topological group G is commutative. So it's basically the same idea. And the reason is very simple, that pi1 of a topological group, it's group from two different reasons. It's group because pi1 of any topological space is a group, but also you can multiply your passes pointwise, or we can just say it like this. Pi1 is a functor from topological spaces, in fact point to topological spaces, to groups. So even if it was to functor to set, so I always can compose it with a functor to sets. Now if I have a group object and they have functor to set, then this functor automatically maps a group object to a group. It's naturally have a structure of a group. Am I right? Yes, because yes, I have a map from G times G to G, and if I have a functor, I don't know, it's not automatic. It's not automatic. The functor should commute with product, but this happens here. Yeah, so pi1 of G full G times G is pi1 of G times pi1 of G. So you get a map like this, and this gives you the product map. So for general functor, it's not automatic, but for pi1 it works. So, but technically, what does it mean? It means that if we have two passes, we can compose them. This gives us the usual product on pi1. But also, if we have two passes, we can take the pointwise product, like this times this times this, etc. This times this, and this times this. And those are two completely different structure of groups, and they are commute. So the structure of product naturally commute with the structure of composition. And this is so, and this gives us that group object in group. That pi1 of a topological group is in fact a group object in groups. It have two structure of a group, and thus it have to be a commutative group. So there is funny was it satisfactory?
Yes.
Okay, so it's funny thing here. So this argument, it looks like a bit abstract, but okay, we can make it a little bit more concrete. So we have to prove something by hand that a so we have two products. Yes, say we have the dot product and we have the star product. We want to prove that they're the same, but instead of proving that, okay, what we actually want to prove, we want to prove that AB is equal to BA. So we have this product of pi1, we want to prove commutativity. And what we actually prove is that A times B star C is A times B. Oh, no, I want to say different. We also prove this, but what we actually proved here that A star B times C is A star times B dot A star times C. And similarly to the other way around. and it's rather easy to check those two things directly. Oh, so this equality and the other equality directly, more or less by hand, and then we get this equality, which is which is harder to check directly. And for a long time, I thought that there are kind of two proofs of this. So there is a there's another proof that directly gives an homotopy between one composition and another composition using the group structure. So this it is much more convenient to say this another proof in the setting of proving that pi 2 is of X is commutative group, but basically they are the same. And I always for a long time thought that the like two actually different proofs, and I didn't saw the relation between them. It looks that here we do something on the topological level, very little work, and then on the algebraic level we do all the work. This is something very general and algebraic. And here it looks that we did something much harder on the topological level. And they finally was convinced that in fact they are very similar proofs, if not the same proof, because you can do this exercise of proving that abelian groups in abelian. Yeah, maybe we'll even say something about how it works. So you want to prove that A times B is equal to A star B and their commute. So you do it something like this. You do A star 1 times 1 star B. And then when star is this other product. And then you use the fact that the two products respect each other, and you get that this is A star B. And then you do similar thing but to the other direction and get that this is B times A. So you do it in several steps. And in fact, when you look at the proof for homotopy theory, so I don't teach your course in algebraic topology, so I will not repeat it, but those of who know it or will know it, you see that this homotopy also have several steps. You can imagine it like this, so some several steps, and each of the steps of this homotopy corresponds to one of the steps here. So in fact, those two proofs, the topological proof and the algebraic or categorical proofs, are basically the same.
What is the difference? What is the star product and what is the dot product?
So when we talk about the general abstract statement, that if we have, so yeah, let me call this star and then it will become clear, is that if we have two star or group objects in group, so we have one set with two structure of a group, then which should be compatible, which are compatible, and then they coincide and both commutative. So then they're just two abstract notions of product. And if we're talking about commutativity of pi 1 of g, then say the dot product is a standard product in pi 1 of x for any x, and the star product is coming from the product structure of g. Or if you're talking about commutativity of pi 2, so if you know that pi 2 is maps between disks, so you can like compose them like this or compose them like this. But this only if you know the relevant algebraic topology. So those two statements are not, so the two proofs are not so different. But yes, anyhow, it's nice thing to know that group object in groups is abelian group. Okay, any questions? No questions? Okay, so I looked at the next chapter and I see that most of it I probably will not really need, and it's probably too complicated. So I will just talk about localizations of category. So basically, yeah, we'll start. Yeah, the first part is too complicated, and I will not really need it later, so I will skip it. So we start with localizations. So what is a localization of a category. Um, so what often happens in category theory? You have, and maybe this is the first example. So until now, basically all our examples of category was um, ob- objects of a category was set with some additional structure, or maybe in case of shifts, maybe it's not necessarily not exactly set, but some correspondence, but something very explicit that we can describe in usual language. And maps was actual transformations between two between the corresponding set sets or objects. So it was really all this terminology of a category looked really relevant, except of one point when we discuss the opposite category, which is if you start with some very natural category, the opposite category is something completely abstract, but yet yes, all the rest was rather explicit on the rest of the examples. And the example that I'm going to talk now about is very so yeah, it's somehow inherently very abstract. So the maps between two objects will not in any sense maps. Or at least yeah, it will be very hard to think of them as maps. So you have category C, and you have certain maps that are not invertible, that are not isomorphism, but you want them to be isomorphism. You want to think of them as isomorphism because they're not that bad, and somehow you want to allow to inverse them. And you get the notion of a localization of category. So this is something that you're very much familiar with when you talk about, say, monoids or rings or yeah, etc. Yes, so when somewhere in the third grade you want to define integer numbers, what you basically say, you say, okay, you know what are natural numbers, you know how to add them, and you kind of have problems with subtraction. Yes, so you cannot always subtract them. So you say, let's add by force all the negatives of all numbers and make it work. And it's not that hard. And of course, soon after that, or maybe some people will suggest to do it even soon before that, you already know, say, what are the integer numbers, and you want to, and you can multiply them, but you cannot divide, so some things are not invertibles, and then you come here. And yeah, it's continue throughout mathematics, so basically the next stage is, how is it called? Localization of a ring over a set of morphisms. It's used widely in algebraic geometry. So you're very much familiar with this procedure, and in a sense, this case will be quite simpler because you don't have another operation to care about. So if you talk about rings and you want to localize them, so you localize a product, but you still have in the background the addition. So it might make problems. And here we localize, but just one. So we want to invert with respect to one operation, composition, so we don't talk about, say, abelian categories where we have also addition of morphisms. So we just have localization. So we want to define S inverse C when S is subset of more C. More C, if I don't write more AB, I mean just a collection of all morphisms in C for all any two objects. I put them all together. And the best way to define such thing should be categorical way, namely somehow define it by some universal properties or some initial objects, etc. And there is one technical problem for us, that we're now defining a category. And the collection of all categories, as I said before, does not really form a category, but form a two category, and we didn't discuss what it is. So I cannot use the language of category theory in order to describe a property as a category. But I can mimic it because at the end I will be able to use it. So there is a notion of two category and there is a notion of initial object there. So, but I will just mimic it. And what is the idea? Is that I want that I want to have a functor from C to here, of course, that will make all the morphisms in S invertible. And I want it not to do anything else. So I want it to be universal in some sense. So what does it mean? It means that if I have another category D, so what I want to say that if I have another category D and a functor here, I want to say that there exists a unique functor like this, such that this diagram is commutative. But of course, I have some problems because for diagram to be commutative, yes, it's not really. I need to of categories to be commutative. I need to explain what does it means. It's not. It's so I can tell you what does it mean. It means that we have functor like this and functor like this, and their composition. I don't want it to ask to be equal to this functor, but it should be isomorphic to this functor. So I need to add this isomorphism as additional data. And if I would have more complicated diagrams, then of course I will have to add to add something about this additional data. But since it's very simple diagram, I just want another isomorphism. And what and yeah, so basically I want this, and then I want to claim that this localization is unique up to a unique equivalence, and this unique equivalence is unique up to a unique isomorphism that satisfies something.
Rami, also the uniqueness of this functor is only up to an isomorphism, right?
Yes. Yes. So, but in this case, there is an easier way to describe it, which is equivalent, but I think it's simpler to understand.
Rami, in the classical sense of localization, you had a requirement in the universal property that that every element in S
in
is
S goes
going
to
to
invertible elements.
invertible
Yes.
element.
Yeah, I said it. I didn't write it, but I said it.
Okay, I didn't notice you
Mhm.
said it. Okay. So what does it mean in this sense that every
That any
morphism is
morphism in S goes to invertible morphism. This is okay. Goes to an
okay?
isomorphism.
Thank you.
This doesn't change. But yeah, the problem is a bit with this universality. So let me phrase it a bit differently. Um, and here is a way. So I have the category of all functors. Okay, definition. Let C be a category S in more C. Now I have E, we have a functor like this, say F, such that F of S inside inv. So suppose I have such a pair. So now I can consider the category of all functors from E to D for some category D. And I can consider the category of all functors from C to D. Here it is full subcategory of all functors satisfy f of S. F is a bad name, sorry. We already have it. Is inv D, I mean all invertible morphisms in D. So clearly I have functor to this direction, just composition with F. First perform F, and then, sorry, yes. First perform F, and then perform this functor from E to D. And once the morphism is invertible, it will go always to an invertible morphism. So isomorphism always maps to isomorphism. So let's call this large functor with some name. How we call it? I don't know. I know how to call it. We first perform F and then perform something else and call it like this. So we say that F, let's like this diagram is the is a localization of a localization S inverse C if this is equivalence of categories. Yeah, so what we actually want? We want that to define functor from C that maps morphisms from F to invertible ones should be just the same as defines functor from here. Yeah, so what does it mean that there exists a unique thing like this? It just means that it doesn't give us any new information, so all the information is here. So it's exactly saying that this is equivalence of categories. So you can translate it to this language of universal object, but yeah, it's the same, but I think this is easier to comprehend. So of course now there is an exercise as localization is unique up to a unique up to a canonical equivalence. Yes, equivalence is unique, satisfying something. Yes. How? Oh, it's unique up to isomorphism. Yes. So, but on the first level, just prove that it's that the localization is unique up to an equivalence, and you will see that this equivalence is basically unique. Okay, so now there's another thing that one has to prove. Theorem that localization actually exists. In general, when you define something by universal properties, of course, it doesn't have to exist. But since we are working here in very general language, so we take a general category, general set of morphisms, we want to invert it. So usually there should be no problem. We want to invert it in the world of all possible categories, and there are many categories, so not a problem. So the construction is, yeah, this theorem is basically also an exercise. Construction is rather straightforward. So it reminds the construction of localization of monoid. It's maybe, yeah, there is a construction of localization of monoid, which is rather simple. Even non-commutative monoid, yes, it's rather simple. And there is a construction of localization of a ring, which is in general very complicated. So if you have a set S of elements in a ring A, the localization going to be very complicated. And the reason is that when you start to do localization naively, so first of all, you cannot just say let's take elements that look like A over S. This does not even work in a monoid because the product is not commutative, so you have to write it like this, but then you also should write like this and like this and like this, etc. And when you do it like this, it's completely not clear why it will, how to add such things. And basically you have to take the linear span of all such things up to some relations. But then it's completely not clear why, no, sorry, I confused with something else. Yeah, this is okay, yes. The complicated thing is actually not this. Complicated thing is how to go to a field or skew field of fractions. And this is disaster. Yeah, so yeah, but still, I think localization of a ring is a little bit more complicated localization of category because here we have to care only about one operation. So not that bad. It's more or less like localization of monoids, but a little bit more complicated than that. So basically, we want to consider things like this. So if we have two objects and we want to consider maps between them, so we can write many arrows like this, these zigzags arrows, and the arrows that goes in the wrong directions have to be from S. And when you have two such things, you know how to compose them. You just plug them in, and here, sometimes you will have to compose. But of course, when you find it like this, you have to be a little bit more careful. You have to take some, you have to quotient by some equivalence relations. Yeah, because if one of the arrows is identity, you want to ignore it, and etc. And okay, and there is a question: what you start with? You should consider both cases, or 4 different cases. You start with direct arrow, inverse arrow, and end with direct arrow, inverse arrow. And there is some work to do here, but it's not really hard. Okay, so any question about localization of categories? No? Okay. So so okay, let me give one simple example and then complicated example. One simple example, when you have topological space, and so do you know what is the homotopy equivalence of topological spaces? Sorry. Okay, but basically this is a cheating example. So let me do the cheating. So let's talk about the homotopy category. So what is a homotopy category? It's a category whose objects are topological spaces. Just a moment. I need to go back to here. So when we talk about localization of a category, so I give this abstract definition, and then I try to give some hint about the construction. But one thing that you see about the construction is that the objects are still the same objects, and what you did, you just add lots of new morphisms. And this is very common in category theory. Even if you, in this case, kind of wanted to identify between two different objects, if two objects have a map in S between them, you want to think of them as isomorphic. But you should never identify objects. There is no reason to do it. You can always add morphisms to make objects that was not isomorphic before isomorphic now. So in general, if you have this temptation to identify objects, usually it's better just to add morphisms. So you have homotopy. So the homotopy category is a category whose objects are topological spaces, and maps, if we have two topological spaces, k, x, y, so maps are all the continuous map between x and y, modulo an equivalence relation. And the equivalence relation is homotopy, so two maps are the same if they are homotopic one to the other. So I assume you all know what is homotopy of continuous map. Yes? Everybody know this? Good. Now consider this functor. The nice thing about this functor that now many morphisms here F that was not homeomorphism before, that was not isomorphism before, become isomorphism here. So this is basically the definition of homotopy equivalence. Yeah. So a map is homotopy equivalence if it is isomorphism in this category. So it means that we have an inverse map such that both composition not equal to identity but homotopic to identity. And okay, now I didn't check it, so I should have. So maybe I will check it during the break. So I'm pretty sure that this is basically a localization map. So you just a localization functor. So when you localize by all the homotopy equivalence, you get this category. I'm pretty sure it's true, but maybe I will do now a break and will be more sure after the break. Any questions before the break? Okay. Who is back? Somebody is back. Ah, I see guys back. I see Yotam and Nomi. Leo is back.
I'm here.
And Or, are you back? Not Leo, but Or. Or? Or is not back. And Vanetta is back. So we will wait half a minute for Or.
I'm here.
Yeah, I see. But I still don't hear from Or. So when Or will be back, we can start, or we'll just wait another 20 seconds. Okay, it's already more than 10 minutes. So I think we can start. So I think I checked it. So the statement that I said here is correct. So let me repeat it. So we have the functor from the category of topological space and to the homotopy category, and the say exercise with star to show that this star functor is a localization by the class of homotopy equivalences. And okay, this is maybe very nice, but this is a bit cheating, yes, because we started with a functor. We say we define the homotopy equivalence to be the thing that maps to isomorphism under this functor, and then we say that this functor is a localization. So it's not always, it will not always work like this, but this is not interesting case of localization. We first define the localization and then define the set S that we want to localize by. But and yeah, and in this case, it was kind of easy to define localization because you could have just defined them as define morphisms in localization as morphisms modulo some equivalence relation. But this is in fact rather rare. So if you slightly change the settings, it stops to be true. And maybe the closest example to here is what's called weak equivalences or weak homotopical equivalences. So if you know what is pi n, I will first say in language of pi n and then in general, in other language. So definition, f from x to y is called weak homotopical equivalence if f star from pi n x to pi n y is homotopical, is isomorphism. And I will just say what it actually means. It means that so I can consider all maps up to homotopy, from Sn to X. So the collection of maps up to homotopy from Sn to X is actually pi n of X. But I will not define the group structure now, so I just consider it as a set. And of course, I have a natural map just by composing with F. Let's see, you first perform this map and then perform F. So it means you compose like this to K from Sn to Y. Yeah, so I wanted this be bijection. So equivalently. Yeah, so this is a definition and this is an equivalent way to phrase it. Okay, and then there is another interesting notion of the weak homotopical category, which you take weak homotopical equivalences and you invert them on top, and this is a weak homotopical category and it's harder to describe in such a way. So in fact, in this case, it's not that hard, but still harder to describe directly. So those two examples have very nice analog in the world of complexes. So chain complexes of abelian groups of vector spaces, so in fact in any abelian category. So do you know what is a chain complex? Somebody does not know what is a chain complex? So chain complex in say of say abelian groups is a sequence of abelian groups C1, no, not like this, I want to like this. X1, X2, X3, X3. So probably in this direction it will be called cochain complex, but I don't care, etc. And now I can have another chain complex, Y1, and a map between two chain complexes. It's a map such that this big
Rami, you
diagram is
forgot, I
commutative.
think, to say the condition. Those
Yes, of
condition.
course, I forgot to say the condition. So the maps here are called differential, so usually we'll just call them D, but if you want to be exact, you will call them D1, D2, etc. And now you want the D first to do D1, say, and then to do D2, or in general, just do twice D, will be 0. Okay, so this is part of the definition of complex. And you see that this is basically equivalent if you're working in a abelian category. So this is equivalent to the fact that the image of D is inside the kernel of D, and the complex is called exact sequence if you have an equality here. And you have the notion of homology, or in this case cohomology. Yes, it depends on the direction. If the direction goes like to the upper side, then it's called cohomology, and if it goes backwards, it's called homology. And is the definition of never mind homology or cohomology. You just measure how much they're not the same, so you take kernel modulo the image. So now you have, so basically you can start with any category C, and you can make out of it the category of complexes over C. Oh, not any category, but say, so let C be abelian category. In order to define, you don't need it to be abelian, you just need to have 0, but let's do abelian category. So we can define the category of complexes over C to be the category of complexes with objects in C, and morphisms between morphism between two complexes defined to be set of morphisms such that the diagram is commutative. Now this is first thing. Second thing, so if we have if phi from xi to yi, phi, let's say phi equal to phi I, is a morphism. Now we can define map on the homology. Sorry, I didn't denote this thing. So if, so maybe, sorry. So 1.5, no, I will write it downstairs because I don't have a place here. 1.5, no, sorry, let's do it here. I have this thing, I forgot about it. Okay. this will be 3, this 2. If xi in C, define hi of x with a kernel of di modulo image of di minus 1. Yeah, so I said if we have a complex and the image is always inside the kernel, now I have to define what is modulo. So if we have in a Boolean category, if we have object and sub-object, then the quotient, then we can define the quotient. It's basically, if we have object and sub-object, we have a map between the sub-object to the object by definition, and the kernel is and the quotient is just a co-kernel of this map. Yes, so is it okay? This notion of a, this notion of a quotient. Everybody is okay with it? Okay, I assume that yes. So now if we have morphism of two complexes, I can define phi I from hi of the first one, so not phi I, but phi lower star. From hi of the first one to hi. Yeah, I should write I upstairs because we're talking about cohomologies of so this is x and this is y. So how do we define it? So we have a map between xi and yi. It commutes with d, so it maps the kernel to the kernel, the co-kernel to the co-kernel, so it induces map on the quotient.
Rami, you said HI, but where is the I?
You mean why I should write I here?
Yes, I think, no?
Yes, but you can be lazy about it, but yes. Sometimes you just take the direct sum of all homologies and consider as one graded object, but yes, for all I, for any I, you have this map, and you usually just denote it by phi lower star. Also, there are very many different maps that have the same name, but this is what we usually do. And for, I would say that phi is quasi isomorphism if phi lower star is isomorphism. So is this definition clear? Yeah, so
What is the word that starts with Q there?
quasi.
Thanks.
Except in tree, what is the map? How the map is defined?
So I basically
star map?
take the map phi I and restrict it to the kernel of D. And of course the image will lie in the kernel of D. And then I notice that it also maps the image of the previous D to the image of D. And so it's induced map on the quotient which we'll call phi I star. So why I'm telling you all this? Because so it's very often in homological algebra, say in general, and specifically in algebraic topology, that you have some procedure that defines you some complex. And often you see that this is not very good procedure. It depends on, or either it gives some very huge complex that you cannot really compute, or it depends on some choices, or sometimes both. So, and you often don't really care about this complex. You care only about the cohomologies, or the homologies, depending on the direction. So if you're familiar with the notion of homology of a topological space, it's defined exactly in this way. You construct some big complex out of this topological space and then takes the cohomologies or homologies. And there are many different definitions of these big complex, but they will always give the same answer on the level of cohomologies. So you often want to say that yeah, you don't really care about the complex, you just care about the cohomology. So one way to do it is that okay, you define sequence of abelian groups or graded abelian group or the HIs, or if you're working in some other category, graded object in the category, just sequence of objects in some abelian category. And this is good for many purposes, but when you look a little bit more carefully, you see that it's not that you completely do not care about the complex, because each time you, or maybe you mostly care about the groups themselves, but it's not that the complex itself is completely not very well defined. So you have many different versions of the complex, but each time that you want to prove that the homologies are the same, what you do, you actually construct a quasi-isomorphism between the two complexes. Or maybe not each time, but in many cases you construct quasi-isomorphisms. And sometimes you can construct quasi-isomorphism, but usually there is a good reason for this. Because you say you have three definitions, and those are two equivalent because you can construct quasi-isomorphism between the complexes. And those two are equivalent because you can construct quasi-isomorphism between the complexes. And those two are also equivalent because it's transitive, so it will give you the same homologies, but quasi-isomorphisms are not transitive because they can go to different directions, and then you cannot, at least in a natural way, to find a quasi-isomorphism from here to here. But they're still kind of quasi-isomorphic, so quasi-isomorphic through something. And so you want to actually see what you constructed. You constructed more than just a complex. You constructed, sorry, less than just a complex, but more than just sequence of abelian groups. And you kind of constructed a complex up to quasi-isomorphism. So you want to be able to talk about this category of complexes up to quasi-isomorphism. And maybe the first naive way to say, okay, let's do equivalence classes of complexes, and we will say the two complexes are equivalent if they are quasi-isomorphic. So this is not equivalence relation, so you close it to be an equivalence relation, and then you're happy. But of course, then you lose all the categorical structure. So what you actually want to do, you want to localize by quasi-isomorphisms. And maybe this is 5, the definition of derived category D of your category C is you take the collection of all the quasi-isomorphisms, you invert it in C. So in this way, this is not very easy to work definition because I defined localization in general and prove, or even didn't prove, but stated its existence, but it will be very hard to work with. I will try to say a little bit better way in some time, maybe today, maybe next time. But this is the notion of the derived category, which is very, very useful in algebra, in the algebraic topology, and etc. Okay. Any questions about the definition of derived category?
In the definition, you used chain complexes, right?
Mm-hmm.
So you need only that C is an abelian category and the rest just works?
Yes, and sometimes you even don't need that, but then it becomes more complicated. At this point I didn't prove anything, I just defined. So it's very easy to see that everything works. But if you want to prove some theorems, so sometimes it will be easier to do it for some explicit version. So derived categories of modules over an algebra, or derived category of abelian groups. There is a book by Gelfand and Manin when they do everything carefully, and they do it for general abelian category, and you can see that at some point it will be easier if you can just take an element in your group, in your object, and do something with it, and they cannot say it because they work in general abelian category, so some theorems become harder there.
Can you please give maybe
An example.
I am greedy. I want, if it is possible, that not only one example. Thanks.
I will try, but yeah, it's not. I will give, I think, more example of localizations. I will try to do. Okay, I will try to give some examples of derived category. It's not very simple, unfortunately. But okay, maybe we'll start with very simple example. No, but before this, there is something that I wanted to say some time ago and forgot. So let me say it now. It's not relevant to what I'm saying now. It's just relevant to the past. I don't even know where is the correct place to put it. So maybe when we discuss faithful functors and fully faithful functors, etc., and equivalences of categories. So there is one nice construction in general in category theory that you want to construct an object in some category. Sometimes very explicit category. You want to construct a vector space, and you often will see that many different constructions depends on choices. So you have some set of choices A, and for each A, you give some object X in C. And you often will see in textbooks, so okay, it's easy, or we want to prove it easy to see that this construction does not depend on the a posteriori does not depend on the choice. And what does it mean? It might mean that if you have A and B, so this is XA and this is XB, and it might mean this. And if X and B are A and A and XB are some elements in some set, this is what you want. Yes, you want to see that you actually construct a well-defined object. But if the object is category, you basically never can expect this. Yeah, we talked about tensor product. You have 5 different definitions of a tensor product. So I even didn't choose anything. Or I can choose one of 5 definitions, so I will have 5 different objects which would called tensor product. But here I can give you examples that actually depends on choices. You want to define tensor product. If you have basis of 2 vector spaces, then it's very easy to compute the tensor product. So you say, choose a basis here, define stupidly the tensor product by bases. Yeah, so you have tensor product with you have vector space whose basis is EIFJ. This is the tensor product. We're done. One small thing, we have to verify that if we choose 2 different bases, we get the same object. And we, of course, will not get the same objects. We'll get 2 isomorphic objects. Okay, so we can say that we just need to prove that they are isomorphic. But this is a bad idea, because if we have another choice, so we'll get many, or 3 different isomorphisms like this. So actually we want to be able to construct a map that we'll call IAB, and here a map that we'll call IBC. Here a map that we will call ICA. And we want that the composition will be identity, say. Or you can write it differently. You can inverse one of the arrow and want 2 different morphisms will be the same. And the claim is that this is enough. In this case, if you want to define objects in a category, if you depend on some choices, you should choose. You should have a map between. You should have a map between any 2 choices and this nice coherence relation. And this is enough. And you can ask, of course, why is it enough, and how I from this can get one big universal map. And okay, here is a nice reason. Consider the category, let's call it constructible A. Category whose objects are points in A, in the set of choices. And for any 2 choices, for any 2 elements in A, you have a unique arrow between them. And of course, the composition maps the unique error to the unique error. And consider the category of functors between cont A and C. So what I claim that this nice set of choices together with isomorphism is basically a functor from cont A. Oh, I not consider the category, just okay, yes, consider category functors like this. And consider the category C. And of course, each time I have object in C, I can construct a functor from cont A to C just by choosing all the time this object and take identity. So I have a functor like this. So exercise that this functor is equivalence of categories. And this is exactly means that in order to construct object here, it's enough to construct object here. So formally, it means that we will have to once and for all fix an inverse functor of this functor, and this is rather easy to do. In this case, it can be done explicit. Yeah, it can be done explicitly.
I didn't understand. This method, what does it allow you when you
To
use
construct, to just even explain whether it means that your construction does not depend on choices. So if you construct, I don't know, a number, then it's clear what it means does not depend on choices. When you define this number in two different ways, you get the same number. But if you construct a vector space, what does it even mean to say that this vector space is well defined? If its upper row depends on some choices. So the claim is that this is what it means, that you in this commutativity of such diagrams. And it's actually a mathematical claim with a proof, because if you have a choice of a vector space between also a construction of a vector space for any choice, and you have such morphisms, then you can out of it cook up one vector space. It basically will be the limit over the diagram, but you can cook up a vector space like because this functor is equivalence of category, so you can choose an inverse functor once and for all. For any category C, you choose it, and then any object that you want to construct will not depend on any more choices. It still will depend on one choice of this inverse functor, but this choice kind of nothing should depend on it, because once you have two categories that are equivalent, you want to think about them as the same. So this is
this the cocycle requirement or like schemes?
yes, this thing often called cocycle condition.
Cocycle, okay.
Of course, when you go one level up, so for example, you want to construct some category and your construction depends on choices, then your life becomes tougher, because then you have to have you can have three different choices. So for any two choices, you have to construct an equivalence of categories. For any three choices, those two corresponding equivalences have to be isomorphic. So you have to construct an isomorphism between those equivalence of categories. And for any four choices, there is some additional cocycle condition. I think it will give you the pentagon diagram or something like this. Yeah, I'm not sure. But the idea is that you always should be able to talk about this category or maybe higher category whose objects are A, and you just add enough morphisms to make everything the same, and not too much or there's a minimum amount of morphisms to make everything the same, and then functors from this category to C will be just the same as the category C. Yeah, I said that this is the exercise, but the hint to this exercise, which is also an exercise, is that cont A is equivalent to just the category of one object with one identity map between this object to itself, and this is it. So this is nice to know. Another comment that I wanted to say is that all this theory of localizing category and derived category, and even the example that I gave in the very beginning of topological spaces with homotopical equivalences or weak equivalence, is also serve as one of the motivation to go to higher category theory. Because if you see what happens here, for example, when you talk about the homotopy theory, homotopy category. We said that we identify two morphisms whenever they are homotopic. But when you see this definition, you see it from the point of view of category theory, there is some problem with it. Because the fact that two morphisms, two continuous map are homotopic, it's not just something that can be true or false. It's when it's true, there is some homotopy that proves that it's true. It's like saying the two objects are isomorphic. It's not just a fact, it's some additional information or how they're isomorphic. And there may be more than one homotopy. And each time you see this thing, the best thing is not to identify between those two objects, but declare them isomorphic. So declare the homotopy to be isomorphism. And it means that you have to pass to higher level of categorification. And in fact, the same happens in general localization. When you do this localization, you do all these long errors, you see that you can't just take those errors. You have to quotient them by some equivalence relation. And each time you have equivalence relation, and if this equivalence relation is not just in information, so some objects make two things equivalent, it means that there is some category, higher category that's hiding here. And unlike maybe the previous cases when we talked about, I don't know, the category of all categories, we say it's two category. But here, this thing will have no limit, no end, because if two morphisms are homotopic, you can discuss, you can remember all the homotopies, but two homotopies, they can be equal, they can be not equal, but they also can be homotopy, and it will have no end. So there's homotopy between homotopies, and this is basically maybe the main motivation why people introduced higher category theory. So maybe for me at the beginning, just when I saw the notion of category, it looked very natural to say, okay, we want, if notion of category formalize different topics in mathematics, and category theory is an important topic in mathematics, we need to be able to discuss the category of all categories. And this is a nice motivation, but it's not very important for practical reasons, because you can live rather well without discussing category of all categories. And if you need it, so you just need this one step more, and the next step you always never need. But this localization, both the homotopy category and this localization that I'm discussing now of derived category, it becomes very important to discuss it not just as a category but as a higher category, and this is I think this is the main use and the main motivation for higher category theory. And also this explains why there is so close relation between topology and category theory. You see it better in higher category theory, because when you just consider homotopical, like space X up to homotopy, so what you actually care about is a set of all its points, set of all passes between 2 points, set of all homotopies between 2 passes, etc. So all this combinatorial data of homotopies, etc. Basically, you can reconstruct from it your space X up to homotopy, or up to weak homotopy, never mind. If X is reasonable enough, then you can reconstruct it up to homotopy. So homotopy theory and higher category theory are more or less the same. Okay, now I promised to give some examples of derived categories. So let's do the easiest example, vector spaces. What is the derived category of the category of vector spaces? So complexes of vector spaces, you know what they are. Yes, VR, V1, V2, V0. And now good news. Let me see how I say it. Yeah, okay. So if you have a complex of vector spaces, you also have, you can consider its homologies, H1, or cohomologies in this case, never mind. So H2, etc. And you can consider that the complex just putting zeros here. And of course, the cohomologies of this complex will be just the cohomologies of this complex, because 0 just will not change anything. But this you can do with any abelian category. But just the fact that you have the cohomology the same does not mean that the objects are quasi-isomorphic. But in this case, it is correct. So for vector spaces, any complex is formally split. It's the same as its homologies. It's quasi-isomorphic to its homologies. And the reason is very simple, because if you have vector space V and subspace W, you can always find a space L such that V is equal to W plus L. So all this homology theory, all these sub and quotient and subquotients, they're all direct summands. So you have the kernel here, which sits inside V1, but it's direct summoned. And inside the kernel, you have the image, but the image is also direct summoned on the kernel. And the difference, so you can find the complement, will be just isomorphic to the homology. And each time you have here a map, you can find the pseudo inverse here, a map to the other direction that use defined only on the that projects to the image and then gives a section. Yes, kind of. You do have the axiom of choice. So if you have an onto map, you can make a section. And so you have, for example, you don't have non-trivial short exact sequence. If you have short exact sequence VWL, so sorry, what I did. So this short exact sequence splits. So it's in fact coming from V plus L. It is not canonically splitting, so you have a section like this, yes. It's not canonically splitting, but you don't really care, it exists, and this is the important thing. And so it means that there is no interesting homological algebra in the category of vector spaces. And one way to phrase it is that any complex is isomorphic to such complex. And this means that the localization of vector space, so yes, that you have a functor now from vector spaces to graded vector spaces. Just consider the graded vector spaces from, you can think about it as vector space decomposed to a direct sum, but you can just think about it as a sequence of vector spaces. So you have functors from complexes of vector spaces to graded vector spaces. The functor is homologies, and these functor of course map any quasi-isomorphism to an isomorphism by definition. And the claim is that this functor is a localization functor. This is rather easy to see. So the answer here is very easy. It's just this. Here I'm a bit worried. No, this is correct. So it's just graded vector spaces. So this is the first example. The second example is abelian groups. And here I'm not sure Z models or abelian groups. Yeah, it's also probably true that any complex is formal. Oh, somebody want to say something?
In the previous
Fine.
example, can you explain please why, what, what are the, I didn't understand what are the isomorphisms.
The quasi-isomorphisms, or
I mean, what is the, why is this, why is it a localization?
I didn't explain. But this is also easy. I'm not sure how to do it now, but it is an exercise. Maybe I will formulate it and we can discuss it next time if you will still have questions. What happens here? Yeah, so we have complex of vector spaces, and we have graded vector spaces. So you always, for any category, you have such functor, and for any category, this functor from definition, by definition, factors to the derived category, because it maps quasi-isomorphisms to isomorphisms. And they claim that for vector spaces, you have your equivalence. This is equivalence. Yeah, I didn't explain why it's so, but you have to show that this is a localization functor, that any other functor factors to this one, and this is rather easy. And Guy, you wanted to say something?
Yes, so in Z, not every complex is formal, but every complex
Of
is
three
quasi-isomorphic to something which is formal. I mean, it's in two steps.
Okay, it is formal, but not by
No, it's not.
definition. I think it's
Not in the
because
definition, not in the sense that there is a quasi-isomorphism to
i-
or to a thing of space.
to a graded abelian group, but it is quasi-isomorphic to a graded abelian group.
Yes.
Nice.
If you want an example, you have Z mod 4 going to Z mod 2.
You need Z
And,
mod 4, you cannot do it with Z.
Hmm?
You cannot do it with Z.
No.
Let's start
Wait,
maybe with this example. You have
Z
Z goes to by multiplication by 2 to Z.
No, so that would be formal.
This is formal because so
Everything
the
is free,
cohomologies
so
look like this.
the argument that you had before just works.
So the cohomologies look like this, yes?
Yes.
But you say if you have Z mod 4 goes to Z mod 2 like this.
Yeah. I think that should work.
Now here you do have
Yeah.
kernel. Z mod 2, yes, you're right. And you have a co-kernel. Do you have
No, wait.
co-kernel? No, you
So,
don't.
no,
Go
it
to
doesn't
Z mod
work.
4.
So maybe everything
Go to
is
Z mod
formal, but not always in the same direction. I'm not sure.
No, you're probably right that everything is formal, but there is no just one error to do it. Yeah, what about but Z mod 4 goes to Z mod 4.
Oh yeah, so that works. That works. Right.
So here you cannot find the morphism
You don't have a map
upstairs.
from the Z mod 2 to the Z mod 4, the left one, and you don't have a map from the Z mod 4 to the Z mod 2,
You have maps
the
downstairs.
other way around. You don't
But the
have a
maps
map from the
downstairs
left
are
Z mod
not good.
4.
You have maps downstairs, but they are not good. Yes, they will not make this diagram commutative.
You have a map from the Z mod, the left Z mod, the right Z mod 4 to the Z mod 2. You have a map from the left Z mod 2 to the Z mod 4, but you don't have any of the other arrows.
No, you do have a map like this, but it just will not make the
No,
diagram.
that's not the right map. But that's not the right map. I mean, on homology, it's 0.
Okay, so let's. Okay, so here is a great exercise by Guy. That those two complexes, they are quasi-isomorphic, meaning that there is a chain, not very long one, of length 2, build of quasi-isomorphisms, that's starting here and goes here. But you have to have something in the middle. Yeah, probably like you can do it in any direction you want, but yes. So you can find another complexes and two maps, each of which are quasi-isomorphic, and so together in the derived category they will be isomorphic. But there is no map between them which will be quasi-isomorphic. So is the formulation of the exercise clear? Yotam?
Actually, not at all, but I think I will not understand it in the remaining time. So
No, this will be the best use of the remaining time, whether or not you will understand. Okay, let's try to do it. Not to do the exercise, to understand the formulation. So I wrote here a complex. You see this complex? I didn't write all the other zeros because there are infinitely many of them, but once I have two zeros, I just continue to do zeros. It's not interesting. And this is Z mod 4, yes? It's a group with 4 elements. A cyclic group with 4 elements, yes? Yotam, are you following me?
yeah, I understand what the complex is.
Yeah, and here you have multiplication by 2. And of course, it's a complex because there is only zeros here, no problem. Now you compute the cohomologies. Cohomologies. It's very simple. The kernel of multiplication by 2 is the group of 2 elements, and the co-kernel is also the group of 2 elements. So this is the other complex. Now, before when you looked at this, so you can immediately see, for example, that there is no maps like this. A group of 2 elements cannot be mapped to a free group. But here there are maps, abstract maps, there are maps to both directions. But they are not maps of complexes, so you have to be careful. Now you can try to find map between these two complexes, and you see that you basically cannot find any non-zero map. But nevertheless, the homologies of those complexes are the same. So I can say, here I get 2 objects that have the same graded abelian groups, but they map to 2 different objects in the derived category. But this is not the case. In fact, they have to be mapped to the same object in the derived category. What do I mean? Or not the same, but isomorphic. So when 2 complexes are isomorphic in the derived category, at the beginning we say we just require all the quasi-isomorphisms, all the maps that induce isomorphism of the homologies to become isomorphic. So you can think that if there is no maps between them, they cannot be the same in the derived category. But this is not true, because this relation is not transitive. And when we localize, we make out of it a category, we have to get a transitive relation. It has to be isomorphic, it's a transitive relation. And in fact, if A is quasi-isomorphic to B, and C is quasi-isomorphic to B, then also A and C are called quasi-isomorphic, although there is no quasi-isomorphism between them. They are isomorphic in the derived category, so the image in the localization going to be isomorphic. And this is exactly such example. So here is the exercise. First of all, to prove that they are not, you don't have quasi-isomorphism between them, and then to prove that there's still quasi-isomorphism, meaning that you have quasi-isomorphic, meaning that you have a third complex and 2 quasi-isomorphisms, and this is it.
Much better, thanks.
So it means that in the derived category of abelian groups, basically this doesn't mean, but it is true that in the derived category of abelian groups, basically any object will be isomorphic to complex of this kind. So it could have meant that the derived category of abelian groups is just graded abelian groups, but I don't think it is correct. I'm pretty sure it's not correct. Yeah, I'm sure it's not correct. And the reason is that there are more morphisms. And you actually even can compute them explicitly. This is one of the not many cases when the answer is not trivial, but it still can be computed explicitly. Given 2 graded abelian groups, 2 sequences of abelian groups, you can ask what will be all the morphisms between them in the derived category. And the answer is, first of all the morphisms in the category of graded abelian groups, just piecewise morphisms, or not piecewise, how do you call it? Place-wise, index-wise morphisms. But there are more, something weird, some x's to some direction. Yes, so, okay, maybe next time we try to do, I don't know, I need to think about it, whether it was it or not. So this is a hard example. This is probably the most trivial, most easy, non-trivial example, and it is still a hard one. So we will try to discuss it maybe next time.
I don't know if people know, but this is basically the universal coefficient theorem.
It depends how you formulate it. So if you formulate it the lazy way, so the lazy way is equivalent to the hard way just because of this computation. Yes. So yes, but yes. So this is one thing. Okay, but still another thing that I wanted to say in general before the examples. So okay, before we do them in more details, and this I still can do today. So when we do complex, so we want to localize complexes in C by something quasi-isomorphism, and this is hard. It's hard to do it explicitly. And the trick is to do it in 2 steps. It's similar to what we have in topological spaces. So in topological spaces, we have the notion of homotopy equivalence, and we have the notion of weak equivalence. And here we have the same. If we have 2 chain complexes, we have the notion of homotopy equivalence of chain complexes. So in fact, if we have two chain map between two chain complexes, we have a notion of homotopy between them. And the good thing is that homotopy, two homotopic maps, induces the same map on the homology. So if you have homotopy equivalence, and so once you have notion of homotopy between two maps, then you can just consider it as equivalence relation, quotient by it, and you get the notion of homotopy equivalence, which is very much analogous to the notion of homotopy equivalence of topological spaces. And the homotopy equivalence will be automatically quasi-isomorphism, but not the other way around. So before going to the localization, you can first go to make this homotopy, go to the homotopy category. And then the collection of quasi-isomorphism become much simpler and much simpler to take localization over it. So what do I mean by much simpler? So if you remember from non-commutative algebra, when you want to localize by a set of morphisms, sometimes your life is much easier than in general. So when you want to localize, so you want to write morphisms of this type, but you also want to write morphisms of this type. And in fact, you want to write longer and longer chain, and this can be a complete disaster. But sometimes the life is good when, or in commutative algebra, it's not morphisms, these are just elements, but it's the same idea. So sometimes the life is good, sometimes you can replace any pair like this, S prime A, S inverse A, by a pair like this. And the other way around. And once you have this, you can, or in fact, you need only one direction. You don't need to talk about these long chains, long words with S inverse A, A1, S2 inverse A2, S3 inverse, etc. You just need to talk about chains of length 2. And now you of course have to explain how you take the multiplication, and in the case of algebra you also have to take sum. So here you just need to take multiplication, and it's it's a bit it's still a lot of work, but it's much, it's not a lot of work, but it's still very much it's still not very explicit, but it's much more explicit than in general. So and this is a magic that happens here, and I have no good a priori explanation why. Maybe Guy will know. If you start with this category of complexes, the quasi-isomorphism do not satisfy this OR condition. So this condition called OR condition. So if you start with quasi-isomorphism, it does not satisfy the OR condition, it will be disaster. On the other hand, if you just consider homotopy, it's not enough. But if you consider homotopy, then the quasi-isomorphism satisfies the OR condition. So maybe next time we want to define the OR condition. I probably will not prove anything that here you do get a OR condition, but I will state what it actually mean on the practical level, and I will explain what does it mean homotopy of morphism of complexes, and then maybe we will also do the example. Yeah, I'm just not sure if maybe there are other interesting things that we want to discuss, and this is a bit advanced. So. But it is very important part of category theory, the notion of derived category. It's in fact very important part of mathematics. Homological algebra modern homological algebra is built on this idea, or maybe not that modern, like half a century ago. Homological algebra built on this, and today there is more modern constructions, but this is still a good place to start with. Other questions? No questions? So we stop the video.